Okay, so in this problem, we have an example where we have, so there's a frictionless block attached to an ideal spring with a force constant. So this is K. Let's label what we have here. So we have a mass, we have K here, spring constant. We have an initial condition at time equals 0. The spring is neither stretched nor compressed. So that means x of t equals 0 equals 0. So if it's not stretched or compressed, x is our displacement distance, right? So at time 0, x should be equal to 0. Okay, if it's not stretched or compressed. Then it says the block is moving, oh, and then at that time, so v at t equals 0. So at time 0, the block is also moving in a negative direction, so negative 12 meters per second. Okay, so that's actually a lot of information. I know it doesn't really seem like it, but these are some important initial conditions. So we want to find A, find the amplitude, and B, find the phase angle. And then write an equation for the position as a function of time. So I'm going to do this by using the initial conditions. There's also another version of the solution in the notes, but we're going to do it both ways. Okay, so first initial condition that we know that we have. So initial condition, okay, so at t equals 0, x equals 0. We also have one more initial condition, right? At t equals 0, we also have v equals 0, right? So let's look at our expression for x as a function of time, right? So x of t is equal to a cosine of wt plus phi, right? And so if we plug in what we know, right? So it's going to be equal to 0 at time equals 0. So let's do that. X of 0 is equal to a cosine of 0 plus phi. Okay, and that's equal to 0. So we need a cosine of phi is going to be equal to 0. Okay, cool. So what value of cosine are we looking at here? Well, if it's in the center, so it's the block is moving left, and then the velocity is negative. So our sine of phi is going to be positive. And so if we kind of look at the graph, I'm just kind of draw this so maybe to help with understanding. You don't have to do this, but I think that it kind of helps to conceptualize a little bit. So t equals 0, this is our origin, right? And then we have like a, right, negative a, and then we're moving through some phase here. So I'm kind of giving away what it's going to already be, but that's fine. So, oops, let me just do one period. Okay, so this is 1 period t. Okay, so this is up to so t equals 0 to t equals t for a sine function, right? So over here, I have t over 4. In the middle, it would be t over 2, right? And then this would be like, it would be 3/4. 3/4 t. Okay, just kind of for reference. So what's going on here is if I am pushing it back kind of this at this halfway point, I want a phi that's going to be equal to pi over 2. Okay, to make this equal to 0, I have a phi is equal to pi over 2, and I'm shifting this function forward. So I started here, this is where my function was, and I'm shifting, so by this phase, by pi over 2, right? I'm just moving it over. Okay, so then, now that I have my phase angle from that initial condition, what else do I have? So I have a second initial condition where I know this like velocity. So that means that my dx over dt is equal to, oh, sorry, it's, why did I write 0? Negative 12 meters per second. Negative 12 meters per second. I probably said 0 like so confidently too. Sometimes I feel like I'm on Mars. I don't know. Okay, so V naught. All right, so now, so if I want to find my my V naught or my velocity here, all I really need to do is take the derivative of x of t. So the derivative of x of t is going to give me negative WA cosine of WT plus phi, right? Okay, and that's going to be equal to negative 12 meters per second. Okay, so Cool. So what I can do here, so I have WA cosine, and then I have WT plus pi over 2 is equal to 12. Okay, so my goal for this problem was to solve for A. So I can say A is equal to 12 divided by W cosine of, am I plugging in? Yeah, I'm plugging in 0 for t because I know that my t is equal to 0 here. So t equals 0. So W cosine of pi over 2. So what is my W? Well, W is equal to the square root of K over M. We have a simple harmonic motion problem, right? This frictionless spring. And we're given this K value up here. We're given this K and we're given this M. So we can go ahead and plug in 300 Newton meters and then divide it by 200 or 2 kilograms. So it's just like the square root of 150. W is equal to the square root of 150. And then we can plug that in. Okay. So if you plug in all of your numbers, you're going to get A is equal to 0.979. Okay, so we kind of solve for things in this problem out of order, but let's go back and look for what it asked for and make sure we got everything that we were supposed to. Okay, so first it said find the amplitude and the phase angle. So we first found the phase angle actually just by using our initial conditions. We knew that time 0, position was equal to 0, neither stretched nor compressed, right, from the initial position. So at time 0, right, they said that it's starting at time 0, you know, it has some velocity, and then it's at this x naught position basically. So the we have like 0 displacement basically. Okay, so that's what we started out with. And because we knew that, we were able to just kind of use some algebra to figure out this phase angle phi. Then we had this initial condition t equals 0, and then we knew that the velocity, right, at that t equals 0 was equal to negative 12 meters per second. And then we took the second derivative, right, of this expression, this general equation, right, and that's what we got over here. This is just the second derivative, right, of x of t, so dx over dt, or sorry, not second, just the original derivative, one derivative. So then the derivative of dx over dt, set it equal to the velocity that we were given, and then we just did some algebra basically to solve for A, okay? And this is what we got for A. Okay, then at the end it says write an equation for the position as a function of time. So for part C, for the position as a function of time, if we take everything that we have now and we plug it back in, so in this case, if we use our K value, our K value comes out to approximately 12.2. But I'll just write this guy out. So for part C, what we have going on is we have x of t. I'll do the right color. So part C, we have the x of t function, and we're just basically plugging in everything that we found, right? So we have x of t as equal to a sine of wt, right? Plus, no, sorry. We could actually just transition this sine of wt to just, or cosine of wt to sine of wt, because I want to point out something really important here. Cosine of theta plus 90 degrees is equal to sine of theta. So we can change our expression to be just like sine of this, yeah, at the end here, sine of wt basically. So that's what we're going to do for our last step. So because I'm writing this again, cosine of theta plus pi over 2, right, is equal to sine of theta. So we have our expression for the first part. So we have x of t is equal to a cosine of wt plus phi. And then we know that our phi is equal to pi over 2. So x of t is equal to a sine of wt. And we found our a to be 0.979. And then our w sine square root of 150, right, t, x of t. And this is like around 12.2 or so. So that's our final expression for the position as a function of time. Okay, so hopefully this helped clear some things up. I mean, if any questions. We'll go over kind of the other types of problems where we're dealing with just like non spring systems or maybe some torsional spring systems next time.